Okay, so students, today we are going to take up the chapter real numbers, and this is the first chapter in the NCERT syllabus as for the class 10th. And this chapter we have divided it into two concept lectures. The first concept lecture will be taking up the Euclid's division lemma, finding out the HCF, LCM, etc., and the fundamental theorem of arithmetic. While the second lecture would cover the aspects of irrational numbers um, and such things. Decimals would be covered in the second concept lecture. Besides this, you'd also be having a lecture in which we'll be discussing the problems related to this particular chapter, besides the illustrations that we'll be taking up during the course of the two concept lectures. We'll also be taking up assignments, and then there'll also be a doubt class in which in which I'll be taking up the doubts that you have related to the chapter from any of the books that you're pursuing or the assignments that we give out. So let's start the first chapter and the first concept lecture. And the first point is Euclid's division lemma. So what does Euclid's division lemma say? You have studied in your earlier classes about division. So you have a number, say you have a number 36, you divide it with 7, what do you get? You get quotient as 5, and in here you get 35, you get a remainder as 1, right? Now this 36 is the dividend. So we always say that dividend is equal to the divisor. 7 is called the divisor. The number with which you divide is called the divisor. Divisor into quotient plus the remainder. This is an equation that you already know of. Now this has been put in the form of a standard lemma, a statement which says dividend is equal to divisor into quotient plus remainder. This is the Euclid's division lemma. What exactly is a lemma? Lemma is any statement. Lemma is any statement that is used to prove the truthfulness of any other statement. So we consider a lemma to be truth, and using that we prove the truthfulness of any other statement. So that is called a lemma. So Euclid is the mathematician who found it out. So it's named after him, and since it is related to division of two numbers, we call it Euclid's division lemma. Euclid's division lemma will be used to prove other results during the course of this chapter, and we'll be taking it up one by one. So to state it in words, what it says is given two positive integers a and b. If two positive integers a and b are taken, then there would exist unique integers q and r, which would satisfy the equation a is equal to bq plus r, such that r lies between 0 and b. 0 is included, but r cannot be equal to b. It always has to be less than b. So this is the condition on this division lemma. So what it says is, for any two positive integers, here it's 36 and 7. For any two positive integers, there would exist two numbers q and r such that a is equal to bq plus r, where r would always lie between the number 0 and it should be less than b, and it will be an integer, it cannot be a fraction. So remainder is an integer lying between 0 and b, where b is not included. So B is what? B is the device that you are taking. So this is actually called the Euclid's division lemma. What does it mean? For example, if B is 6 or B is 5, if you take 36 divided by 5, one thing that you can be sure of is that the remainder will never be equal to 5, which is the truth, because here when you divide it, you again get a remainder as 1, which is satisfying this. So the division lemma, Euclid's division lemma, is always true. Now where is it used? Euclid's division lemma is used to calculate the HCF of two numbers. Euclid's division lemma as a statement will not be calculating the HCF. There is a procedure or a step-by-step process that we call Euclid's division algorithm that is used to calculate the HCF, but we principally use the Euclid's division lemma in doing that, and hence we say that the Euclid's division lemma is used to calculate the HCF of two numbers. How do we do that? Now here it is. We have the Euclid's division algorithm. What does it say? It says that to obtain the HCF of two positive integers c and d, where c is greater than d, we have to follow the steps listed below. The first step is apply division lemma to the numbers c and d. C is the larger number, D is the smaller number. So C will be the number A that we saw in the last slide. Remember, the dividend is the larger one and divisor is the smaller number. So here C will be the dividend and D will be the divisor. And you apply it. So you have C is equal to D, Q plus R. Since we are applying Euclid's division lemma, so we know that there for any two positive integers C and D, there would exist two other numbers Q and R, where R lies between 0 and D, such that C is equal to DQ plus R. This is what the division lemma is. Once you apply this, you find out what the remainder is. If the remainder comes out to be 0, then D, the divisor D, is the HCF of C and D. This is the process. If R is not equal to 0, that is if the remainder is non-zero, then you have to apply division lemma to the numbers D and R in the next step. So you have the numbers D and you have the number R. You have to apply the Euclid's division lemma to D and R. Now, which one will be bigger? D will be bigger. The divisor will be bigger than the remainder, right? Because remainder is always between 0 and D. So R is always less than D. So D becomes the dividend and R becomes the divisor in the next step. So for two numbers D and R, there would exist two numbers E and R1 such that R1 lies between 0 and R, which is the divisor. This such that D is equal to ER plus R1, right? Then in the second step, what we did was we took the divisor from the first step, which was the number D, and we took the remainder as the divisor in this case. So you have two positive integers D and R. They can be related as D is equal to ER plus R1, where R1 lies between 0 and R. Here the equality sign would hold on R. Here the R1 can be equal to 0 as well. So that was missing here. So there would exist these two numbers R, E and R1. Now again you check whether the remainder comes out to be 0. So you have to check whether R1 is 0 in this step. If R1 is 0, then the divisor, which is E, divisor which is R will become the HCF of the two original numbers C and D. So R becomes the HCF of the original two numbers C and D, and you stop the process there. If R1 is not equal to 0, then you have to go to step 4, which again would mean that you will in this case take the divisor from the previous step, that is R, and the remainder in the previous step, that is R1, and you have to find some numbers such that R is equal to F into R1 plus R2. Now R, R1, F, R2, all these are numbers. They are just symbols. We will be taking up an example with actual numbers, so things will become clearer. But since we are stating what the Euclid's division algorithm is, we are using variable names. So you have R is equal to F R1 plus R2, and you again check whether R2 is 0 or not. If R2 is 0, then R1, which is the divisor for this step, becomes the HCF of the original two numbers C and D. If not, then you have to go to the next step again, where R1 and R2 become the two numbers on which you have to apply the Euclid's division lemma. So in here what we see here is that we are using Euclid's division lemma in each of these steps, and this is a step-by-step process. There is a logic behind each of these steps, wherein you apply the Euclid's division lemma in each step and you check what the remainder is. If the remainder is equal to 0, then you stop at that place and the divisor becomes the HCF. If the remainder is non-zero, then you again apply the Euclid's division lemma on the divisor and remainder and again check the remainder. So this is a step-by-step process. So the step-by-step process is actually called an algorithm. So what exactly is an algorithm? Algorithm is a step-by-step process of what? Applying the Euclid's division lemma. So using Euclid's division algorithm, you are finding out the HCF of two numbers. You can also alternatively say that you are using the Euclid's division lemma. But lemma and algorithm, although they are used interchangeably, but they are not same. Fundamentally, they are different. Euclid's division algorithm is a step-by-step process in which you apply the Euclid's division lemma, whereas Euclid's division lemma in itself is a statement. It's a simple statement which says that for any two positive integers a and b, there would exist two other positive integers q and r such that a is equal to bq plus r, where r lies between 0 and b. 0 included, b not included. So now let's take up a few examples, get out of the theory part and take up a few examples and understand this better. Now what does it say? It says you have to find the HCF of two numbers 55 and 360 using division algorithm, Euclid's division algorithm. In the two numbers, the bigger number would come on the left hand side, that is it will become the dividend. So you have 360 equal to 55 into the quotient. So how do you find it out? You simply divide it. So you get what? You get, if you go with 6, you get 0 and 3. So you have 330 here. 30 is balance. But when you use 7, then the number would come out to be bigger than 360. It will be what will it be? 385. So it will be 6 here and the remainder is 30. So what do you have here? 360 is equal to 55 into 6 plus 30. This is the first step of the Euclid's division algorithm. This is the first step. Now what did the Euclid's division algorithm say? That if the remainder is equal to 0, then the divisor becomes the HCF. Is the remainder equal to 0? No. So in the second step, what do? You take the divisor as the first number, that is the dividend, and the remainder becomes the divisor. And what will it be? It will be 1 here. And how much will be the remainder? 25 will be the remainder in this case. Again, the remainder is 0? No, it is not. So you take the divisor and the remainder, and here you write 30 is equal to 25 into what will it be? It will be 1 plus 5. So you have this now. Again, the remainder, is it 0? It is not equal to 0. So again, you take these two and you have 25 is equal to 5 into 5 plus 0. Is the remainder equal to 0? In the fourth step, the remainder becomes equal to 0. So if the remainder becomes 0, then what do we have to take? The divisor becomes the HCF of the original two numbers. So the HCF of 55 and 360 using Euclid's division algorithm will be 5. Interestingly, 5 will also be the HCF of 30 and 25. It will also be the HCF of 55 and 30. And it will also be the HCF of 25 and 5. How? This is clear, right? This is what the Euclid's division algorithm was. How do we say that this is also equal to the HCF of 30 and 25? Now, if the two numbers are 30 and 25, you will begin the Euclid's division algorithm from this step onwards. So the first step would be this and the second would be this. In that case also, when the remainder comes 0, the divisor will become the HCF of the original two numbers, since the original two numbers that we start off in case of this will be 30 and 25. So 5 will also be the HCF of 30 and 25. What about 55 and 30? Again, when you are taking the two numbers a and b as 55 and 30, your Euclid's division algorithm would start from this step. It will terminate here, and again here the 5 will be HCF of which two numbers? Of 55 and 30. Similar is the case with these two numbers 25 and 5. In this case, there will be just one step in the Euclid's division algorithm, because only in the first step you will be getting remainder equal to 0, and thus the divisor, which is 5, and also the second number will become the HCF. So this is one important thing. When you take out the Euclid's division, HCF using Euclid's division algorithm, for each step, the two numbers, dividend and the divisor that you take, the final HCF will also be the HCF of all these pairs. So 5 will be the HCF of not just 360 and 55, it will also be the HCF of all the dividend divisor pairs in each of the steps coming in the Euclid's division algorithm. Let's take another example. It says, so hopefully you have now got hold of what Euclid's division algorithm is. Now we will be applying the Euclid's division lemma and Euclid's division algorithm in a few illustrations, and we will be checking out how we solve those problems. So let us take the second problem. Now this problem says that we have to find the number by which 546 should be divided to get 7 as quotient and 7 as remainder. So we have to divide 546. So 546 becomes the dividend. So you have 546 as the dividend, and this we have to find, let this number with which it is divided be b. So the number with which it is divided is going to be b, and this is going to be a. This is quotient q, and this is the remainder r. So for any two positive integers a and b, what we can say, there will exist two numbers q and r such that r lies between 0 and b, such that a is equal to bq plus r is going to hold true. So you have b into q is 7 plus r is 7. So you have this relation. Now this becomes a very simple linear equation. How do you solve it? You take 7 to the other side. So you have 546 minus 7 is equal to 7b, which implies b is equal to 539 by 7, which is equal to 77. Hence, the number is going to be 77. This is what your answer is going to be. So here we have used the Euclid's division lemma to solve this particular problem. I hope you got it. Now, next problem. The next illustration says that we have to show that any positive odd integer is of the form 6q plus 1, 6q plus 3 or 6q plus 5, where q is some integer. Now how do we apply the Euclid's division lemma in this particular problem? What does Euclid's division lemma say? It says that for any two positive integers a and b, there would exist numbers q and r such that a is equal to bq plus r. Now how are we applying it here? For any two numbers a and b, so we can take the two numbers as a and 6, right? A, where both of them are positive integers. So a is any positive integers and b we have taken as 6, since b can also be any positive integer. So also for a and 6 we will be able to find out a number q and r such that a is equal to 6q plus r. The restriction on q and r is that both of them are going to be integers, which we have been given, and on r the restriction is that it should lie between 0 and the number b, and the number b here is 6. So r can take all values from 0 to 6. So what are the possible values for r? It could be 0, 1, 2, 3, 4 or 5. Can it be equal to 6? It cannot be equal to 6. R can take only these 6 values. Now for the number a, what will its form be if r is equal to 0? So there are all the possibilities we have to consider and then prove that in all the possibilities the number a will come out to be 6q plus 1, 6q plus 3 or 6q plus 5 if it is an odd integer. A can be odd or even both, right? So the first case for a is that a is equal to 6q plus 0, which is 6q. What is the second possibility for the number a? We know that a is any positive integer. We don't know if it is odd integer. We have said that Euclid's division lemma holds true for any positive integer. So a is any positive integer and all possibilities for it are written over here. What is the third possibility for the number a? it can be a is equal to 6q plus 2. The case 4 would be a is equal to 6q plus 3, and case 5 would be a is equal to 6q plus 4, and the last case will be case 6, and this will be a is equal to 6q plus 5. So these are the 6 possibilities for the number a, right? For each of the values of r we have written. So r can be any of these, so a will be any of these. So we have taken all options into consideration. Now what is 6q? 6q is essentially 2 into 3q, right? 2 into 3 is 6, so you'll get, which makes it an even number. Same is the case here. You take a 2 common, you get 3q plus 1. 3q plus 1 is an integer, and you multiply it with 2, so you get an even number. Any number multiplied by 2 would give you an even number. Similar would be the case here. You get 3q plus 2. Again, since 2 is a factor, so it is an even number. Now, since a is an integer, and if it is not even, it has got to be odd. So in out of all these 6 cases, 3 of them turned out to be even, so this will definitely be odd. All these possibilities are going to be odd. So for an odd positive integer a, it could be 6q plus 1. It could be 6q plus 3, or it could be 6q plus 5. These are the 3 possibilities for any odd positive integer. If it is even, then it will have 2 as a factor and it will be one of these 3 forms. But if it is odd positive integer, the only possibilities for it are going to be 6q plus 1, 6q plus 3, and 6q plus 5. So we have proved here that any positive integer will be one of the 3 forms that's been given. So here we used Euclid's division lemma. Let's use the Euclid's division lemma in solving another question of this nature. So now the next question is that we have to use the Euclid's division algorithm. Although it says Euclid's division algorithm, we are going to use the Euclid's division lemma. But any algorithm or any step-by-step process that we apply to a Euclid's division lemma is going to be Euclid's division algorithm. Hence the question. It says that Euclid's division algorithm is to be used to show that the cube of any positive integer is of the form 9q plus 1, or 9q plus 8. Now, intuitively from the last question, what you would do is you would take a and 9 as the 2 numbers, and then you would be finding out the possibility. So you'll be writing a is equal to 9q plus r will take up values from 0 to 0 and all the way to the number 8, because it has to be less than the number 9. So you'll get 9 cases in that, and then for each case you'll be finding out the cube and figuring out what the final form is, and then you'll ultimately get that it will be of the form 9q plus 1 or 9q plus 8, but that is going to make the problem a very lengthy one. So we'll be acting a bit smart in this problem, and we'll be taking it up with a bit of a twist. Now, since we are being told that we have to find the cube of the number to be of the form 9, so if we take a of the form 3q plus r, so in this case r will be 0, 1 and 2. When we cube the number a, we have to find the form of cube of number a. So the cube of number a will be the cube of all of this, and in this case, since we have a 3 here, the cube will become 27, in which 9 will already be there. So we'll be able to find out the forms of a cube of a number. We could have taken a as anything. The number b as anything. We could have also have taken b as equal to 4, and in that case it would have been of this form. We are perfectly fine if we take this 1, 2, 3, and then you take the cube of this number and find out what the cube of this is. But proving this would become difficult, because again you'll be taking a cube and you'll have to transform it in the form 9q plus 1 or 9q plus 8, which will be difficult because 4q will be 64. So it will become difficult to figure that out. But in here, we have taken the cube, the number b as 3. So the cube simply comes out to be 27, which has a 9. So converting or transforming it into the form 9q plus 1 or 9q plus 8 becomes easier for us. That's why in this case, we are not taking b as 9, but taking b as equal to 3. Now, since we have taken b is equal to 3, three cases here would be a is equal to, we have a is equal to 3q. Now, in this case, a cube will become 3q whole cube, which is 27q cube, which is 9 into 3q cube. This is an integer. So it is of the form 9 into q or r, whatever you want to say, where q is any integer. So this is the first equation that we have. Now in case 2, what do you have? You have a is equal to 3q plus 1. It could be of this form. And in this case, what will a cube be? It will be 3q plus 1 whole cube. And what is a plus b whole cube? It's a cube, you have 3q whole cube, which is 27q cube, plus b cube, which is 1 cube, which is equal to 1, plus 3ab, so 3q into 1 is 3q, into a plus b. So here what do you get? You get 27q cube plus 9q into 3q plus 1 plus 1. This is this one you have written at the end. Now what do you see in this number? In this number you see that 9 is common. And what do you have inside? You have 3q cube plus q into 3q plus 1. I have just taken 9 common from there. So you have this. Now q is an integer, rest of the things are integers. So again this will be an integer and we write it in the form 9q plus 1. This whole thing is written as capital Q. So you have a cube is equal to 9q plus 1. This is the second equation. And what do you have in case 3? Case 3 is a is equal to 3q plus 2. And in this case, a cube is equal to 3q plus 2 whole cube. And what does it equal to? It will be equal to, again, 27q cube plus 2 cube is 8 plus 3 into 3 cube plus 2, 3q plus 2. This is what you get when you open up as per the formula x plus y whole cube or a plus b whole cube. Again, you take this number and this entire thing. This is multiplied, not plus. You take this entire thing together. Again, you have a 9 common. So you get 3q cube plus 2q into 3q plus 2. All of it will come in big square bracket plus 8. This again is an integer. So this becomes 9q. This whole thing is an integer q. You multiply it with 9. So you have 9q plus 8. Is there any other case that you have to consider for the number a? No, because you have taken a, b as 3. So the possibilities for the number a are a is equal to 3q, a is equal to 3q plus 1 or a is equal to 3q plus 2. Had you taken b as 9, the possibilities would have been a is equal to 9q, a is equal to 9q plus 1, 9q plus 2, 9q plus 3, go on till a is equal to 9q plus 8. And for each of those cases, you would have to take the cube and find out whether it is of the form 9q, 9q plus 1 or 9q plus 8. Now, one thing to note is the q here and the q here may not be same. It is just a symbol. So it just means that it will be 9 into some integer. So even if you take capital Q or you write it as K, it doesn't make a difference here. Since we are using a standard in our definition that this is small q, so we have retained it here for better understanding, and instead of the small q here, we have used the larger q, the capital letter Q. So in all the cases, what we see is the cube of a positive integer is either of the form 9q when the number is a multiple of 3, or it is of the form 9q plus 1 if it is of the form 3q plus 1, and it is 9q plus 8 in case it is of the form 3q plus 2. So this, all the cases are covered, and in each case we see that the cube is either of the form 9q or 9q plus 1 or 9q plus 8. This is what we have to prove. We have to show that only one of the numbers n plus 2, n and n plus 4 is divisible by 3. Now what does that mean? It says that for any number n that you take, the number plus 2, that is n plus 2, or the number n plus 4, out of these three numbers only one will be divisible by 3. So in this case, for the number n, we take it of the form n is equal to 3q plus r, which gives us three cases. The first case is n is equal to 3q. When r is equal to 0, this will be the case. The second case is the number n that we have to take will be of the form 3q plus 1, and the third scenario is that n will be equal to 3q plus 2. So these are the three cases that are possible for n if we take it to be of the form 3q plus r, where r lies between 0 and 3 from the Euclid's division lemma. So this will hold true. So there are three cases. Now when n is equal to 3q, what will n plus 2 be equal to? It will be equal to 3q plus 2. And what will be n plus 4? N plus 4 will be 3q plus 4, which is also equal to 3q plus 3 plus 1. 4 can be written as 3 plus 1. Now we take 3 common in here, so you have q plus 1 plus 1. This is an integer of the form capital Q, so you have 3q plus 1. In this case, you have n is equal to 3q plus 1, so n plus 2 will be what? 3q plus 1 plus 2, which is 3q plus 3, which makes it 3 into q plus 1. So you get it of the form 3q. And what will n plus 4 be? N plus 4 will be 3q plus 1 plus 4. So you have 3q plus 5, or you have 3q plus 3 together, and you have a 2 separate. So you have 3 into q plus 1 plus 2, which is of the form 3q plus 2. And in this particular case, you have n is equal to 3q plus 2. So n plus 2 will be 3q plus 2 plus 2, which is 3q plus 4, which again can be split as 3 plus 1. So combining these two, we have 3 into q plus 1 plus 1, which is of the form 3q plus 1. And what is n plus 4? N plus 4 is going to be 3q plus 2 plus 4, which is 3q plus 6, which gives us 3 common, and you have q plus 2, which makes it 3 capital Q. Now these are the possibilities, and in each possibility what the value of n plus 2 and n plus 4 will be. Now let us see what happens in case 1. In case 1, when n is equal to 3q, which means 3 is a factor of n, and hence n is divisible by 3. If it is divisible by 3, I'm going to put a double tick mark. So n is equal to 3q is divisible by 3 because 3 is a factor. What about n plus 2? N plus 2 is 3q plus 2. So there is a remainder. A number will be divisible by 3. The number n plus 2 will be divisible by 3 if the remainder is 0. But in here, the remainder is 2. Hence, we can say clearly that n plus 2 is not divisible by 3. What about n plus 4? N plus 4 is equal to 3q plus 4. Again, here the remainder in the ultimate form, it comes out to be non-zero. So you have n plus 4 as in the form 3q plus 1. The remainder is non-zero, so n plus 4 is also not divisible by 3. So in the case where n is equal to 3q, we have only one number n out of n plus 2 and n plus 4, which is divisible by 3. So here in this case, only n turns out to be divisible by 3. What about the second case? The second case, you have n is equal to 3q plus 1. Here the remainder is 1. Here the remainder is 1. It satisfies the Euclid's division lemma. So n is not divisible by 3 because the remainder is not equal to 0. What about n plus 2? N plus 2, you have 3q plus 3. Can we deduce from here that it is not divisible by 3? No. because in the Euclid's division lemma, r has to be less than the divisor. Here r is not less than, it is equal to the divisor. So you cannot say that this constitutes the Euclid's division lemma. You have to reduce it such that the remainder becomes less than the divisor. So for that, here what we do is we have first taken 3 as common, so you get q plus 1 plus you have 0. So you have n plus 2 of the form 3q and you have remainder 0, hence 3q is divisible by 3. Again, when I say that 3q n plus 2 is divisible by 3, but if I had given you this form, you might have been tempted to say that since the remainder is 3, this number is not divisible by 3. But division lemma, Euclid's division lemma holds true only for r less than divisor. So here, only when r is less than 3 can you call it the Euclid's division lemma. And only then can you deduce whether that number is divisible by 3 or not, or what the remainder is. So here we cannot apply the Euclid's division lemma. So 3q is the ultimate form and this form is divisible by 3. What about n plus 4? N plus 4 comes out to be 3q plus 5. Again, we cannot apply the Euclid's division lemma here because r is greater than the divisor. So you have to transform it into a form such that the remainder comes out to be less than the divisor 3. You go on doing it and you get the remainder as 2, which is less than 3, and in this the standard form is 3q plus 2. Again, the remainder is not equal to 0, hence this is also not divisible by 3. Hence in this case where n is equal to 3q plus 1, only n plus 2 turns out to be divisible by 3 out of the 3 numbers. Now in the case 3, you see that n is 3q plus 2. This is not divisible by 3. So you put a cross here. N plus 2 similarly comes out to be 3q plus 1. Again 3q plus 1 is not divisible by 3. But n plus 4 comes out to be 3 into q plus 0, which makes it divisible by 3. So in this particular case, n plus 4 comes out to be divisible by 3, but not the other two. So what we see is that out of the 3 numbers n, n plus 2 and n plus 4, only one of them turn out to be divisible by 3. The possibilities for the number n are these 3. In case n is this, then n is divisible. In case n is 3q plus 1, then n plus 2 would be divisible by 3. And in case n is equal to 3q plus 2, then in that case n plus 4 will be divisible by 3. So whatever case you take, in all the cases combined, you find out that only one amongst the 3 turns out to be divisible by 3, which is what we had to prove. Okay, so this one is a bit difficult to understand, so you have to be all ears in this question. And it says that if A is equal to xq plus AR, B is equal to yq plus BR, C is equal to zq plus CR, then show that the remainder of A into B into C divided by Q is same as the remainder of AR into BR into CR divided by Q. And using this, we have to find out the remainder of 3 to the power 560 divided by 8. Now, what we have to find out is the remainder in case of ABC divided by Q. Now, what is that going to be? Now, A is given to be xq plus AR. So, you have xq plus AR. You have yq plus BR into ZQ plus CR divided by Q. Now what do we do is, for these two numbers, ZQ would be divided by would be multiplied with both these brackets, and similarly CR is going to be multiplied with these two brackets. So this essentially would be ZQ into XQ plus AR into YQ plus BR plus CR into the same thing, right? XQ plus AR into YQ plus BR. We have to find out the remainder when ABC is divided by Q. So we have simply taken what A, B, C are and we have simply divided it and then opened the bracket. Not completely, but in this way. The whole thing divided by Q can be split, right? The whole thing is divided by Q, or you can split it along the plus sign. So you have the whole thing divided by Q, or this divided by Q plus this divided by Q, right? That is how you simplify. You take ZQ, you multiply with these two brackets, plus take CR, multiply with these two brackets, and you have divided by Q. Now here Q and Q would cancel out, which means that this particular number is divisible by Q, and hence its remainder is going to be 0. The remainder in this case is going to be 0. So we are not going to be concerned about this. We have to find the remainder, right? And the remainder when this number is divided by Q is going to be 0. So we can ignore this part. Since we are not concerned about what the quotient is, we are just concerned with the remainder, and the remainder has turned out to be 0. So you write it 0 and you can simply forget about it. What about this number? Again, in this number, it can be split. Now, this exactly is not equal to what I'm going to write, but I'm just talking about the remainder. So the remainder would be C, sorry, it will be CR into U, expand it, right? So you get X, Y, Q square plus X, you have X BRQ plus ARYQ plus AR into BR divided by Q. Now what you see is for all these numbers there is a Q, right? So in each of these cases, sorry, you don't have Q square, you have Q. So in each of these cases, you can take Q common. So it will be equal to CR by Q into Q common. You have XYQ plus XBR plus ARY, right? And you have ARBRCR divided by Q. This number, AR into BR multiplied by CR will give you ARBRCR divided by Q. In this case again the remainder comes out to be 0, so we are least concerned about this portion because the remainder again comes out to be 0. So the ultimate in the ultimate uh, number that we have, this is not going to contribute towards the remainder. So this remainder would also be 0. I'm talking about the remainder. The number as such is not 0, but the remainder when it's divided by Q is going to be 0. So we are not concerned. Now when ABC is divided by Q, the remainder will be same as that when AR into BR into CR is divided by Q. This is what we have to prove, right? When we started with ABC divided by Q, what we ended up with is the remainder when ABC is divided by Q will be same as the remainder when AR into BR into CR is divided by Q, because the other portions of the number we see that they are divisible by Q, so they will not contribute towards the remainder. Only the product AR into BR into CR will contribute towards the remainder. What will the remainder be? Whatever comes out when AR into BR into CR is divided by Q. The remainder that comes out would be same as the remainder when A into B into C is divided by Q. This is what we had to prove. Now, how is it going to be helpful in solving the problem is what you have to take now. Let me just erase this portion. I hope you got it. Now we are going to see how we are going to use it in the second part of the question, which says we have to find out the remainder when 3 to the power 560 is divided by the number 8. So we have to take it. This particular lecture would also be available in your content section. So in case you have any problem in understanding any of the portions, you could just revisit it. And when we have the online doubt class, you could probably bring that up and we can take this up once again in case you're not able to follow it. So I would request you to please go through this particular section once again when you go to the content section and you pick up the lecture. This will become available to you once the class gets over. So you can just have a look there and try to understand it. In case you're not able to do that, then after the second concept lecture, we'll be having a doubt class. You can take that up there. Okay. So this is a bit difficult question. So even if you're not able to follow it completely, I think you would do that if you just revisit it in the revision or in the video that we will be making available after the class. So now we know that for number a such that a is equal to x cube plus ar, b is equal to y cube plus br, and c is equal to z cube plus cr, if it is divided by the number q, then its remainder will be same as ar into br into cr divided by q. This can be extended to more than 3 integers. Here we used only a, b, c, but this will follow for numbers a, b, c, d, e, f, g, h, whatever it is. So a into b into c into d by q will be same as the remainder when AR, BR, CR, DR are divided by the number Q. So how do we use it in this particular question to find out the remainder when 3 to the power 560 is divided by 8? Now, this can be written as 3 square to power 280 divided by 8. Because you have a to the power m to the power n is equal to a to the power m into n. So here m is equal to 2 and n is equal to 280. So 2 into 280 is 560. So you can write it like this. And what is this equal to? It is equal to 9 to the power 280 divided by 8. Okay? So this is what it is going to be. Now what is 9? 9 is 8 into 1 plus 1 to the power 280 divided by 8, right? This is what 9 is. So what this essentially is 8 into 1 plus 1 into 8 into 1 plus 1 into 8 into 1 plus 1. How many times? 280 times you multiply the same number. This is what power means, right? It means you have to multiply this number to this number 280 times. So this is what it is. Now you compare it with the question. A is of the form x cube, q is this, x cube plus this is AR. This again is y cube. Here x and y are equal. Similar is the case with AR and BR are equal, but the form is this. Let it be Z. Okay, I don't know where it will end. I just write it as Z. So what do you have? The result says that if A into B into C is divided by Q, the remainder in this case will be same as the remainder when their remainders or when AR, BR, CR are multiplied and divided by Q. So what will be the remainder when this entire number is divided by the number 8? The remainder will be same as the remainder when AR into BR into CR into ZR is divided by 8, right? The remainder when 3 to the power 560 is divided by 8 will be same as the remainder when AR into BR into CR into ZR is divided by 8. And what are AR, BR, CR? All of them here in the case above, all of them are equal to 1, right? All of them are equal to 1. So the remainder will be same as the remainder when 1 into 1 into 1 into 1 is divided by 8. So what is 1 into 1 into 1 into 1? It's 1. So the remainder when 3 to the power 560 is divided by 8 is going to be the same as the remainder when 1 is going to be divided by 8. And when 1 is divided by 8, the remainder is going to be 1. Right? There will be no quotient. Whatever the number is, it's going to be the remainder. If you divide 1 by the number 8, the remainder is going to be 1. Why? Because 1 is equal to 8 into 0 plus 1, right? When 1 is divided by 8, the quotient will be 0, but the remainder will be 1. So the remainder is 1 when 1 is divided by 8 and this is equal to the remainder when 3 to the power 560 is divided by 8. So we have used this particular result to find out the remainder when 3 to the power 560 is divided by 8, and in our case it turns out to be equal to 1. I hope you got this question.